In a cosmos where distance is measured not in miles but in years of light travel, there's a star whose journey to us defies the usual cosmic scale. It is Earendel, a luminary so distant that its light left it more than 12 billion years ago. By comparison, the light from this star began its journey to us when the universe was less than 1.4 billion years old. It crossed the vastness of space-time to reach us here on Earth. By comparison, the Sun is only 8 light minutes away. At the same time, the Earendel light reaching us has been traveling through space since the earliest life forms formed on Earth. Discovered by the eye of the Hubble Space Telescope, Earendel emerged from the darkness like a clue from the greatest detective story in history. It's not just a star. It's a record breaker, the most distant star we've ever seen. Earendel's light has traveled more than 12 billion years to reach us, starting when the universe was barely 1.4 billion years old. So how did we manage to detect such a distant object, and what does this discovery tell us? In our desire to map the cosmos, astronomers have long sought to push the boundaries of observable universe. This domain is defined not only by the capabilities of our instruments, but also by the speed of light itself. On this cosmic horizon, every star and every galaxy is a potential beacon of the past, inviting us to uncover its history. Meet Earendel, a star at the very edge of this observable frontier. Its light, which occurred more than 12 billion years ago, gives us a rare glimpse into the era of the universe's history that's virtually unexplored. Contrary to conventional standards, this celestial was given a proper name from the beginning, indicating its rarity and significance. The star was christened Earendel, the name of an Anglo-Saxon origin meaning morning star. The name Earendel is particularly appropriate because it symbolizes the star's role as the harbinger of the cosmic dawn. The cosmic dawn refers to the period in the history of the universe several 100 million years after the Big Bang, when the first stars and galaxies formed, ending the cosmic dark ages and filling the universe with light for the first time. The Hubble Space Telescope was the instrument that brought Earendel into our field of view. Hubble's sharp vision, peering across the vast reaches of intergalactic space, captured an image of this distant star. The initial observation was no ordinary discovery. It required the alignment of cosmic forces, the deflection of light through gravitational lensing, and tireless data analysis by astronomers who decoded signals amidst the cosmic noise. Earendel appeared before us not as a fiery disk, as stars are often depicted, but as a luminous point whose details are obscured by the mist of time and space. Nevertheless, even this faint image is a treasure trove of information, the starting point for a journey of discovery that goes back to the earliest chapters of the universe itself. In the history of astronomy, few instruments have revolutionized our view of the universe as profoundly as the Hubble Space Telescope. Earendel's discovery was the triumph of this great observatory. Astronomers, using Hubble's advanced optics, explored the universe looking for faint glimpses of light from the oldest stars. It was like looking for a needle in a cosmic haystack. Wide Field Camera 3, the workhorse among Hubble's suite of instruments, played a key role. Its sensitivity to ultraviolet light, which is often blocked by Earth's atmosphere, allows it to capture the high-energy glow of distant stars. The task was enormous. Earendel's light during its marathon journey through space had dimmed and shifted to the red side to a fraction of its original intensity. Its detection required not only the right instruments, but also a confluence of favorable conditions. Scientists have always sought to unlock the mysteries of the distant universe, to look deeper into the cosmic expanse. Arundel's discovery represents a significant step in this direction, as the detection of distant galaxies has historically been a difficult task. Usually, when astronomers turn their gaze to these distant corners, they discern only the brightest beacons, quasars, and blazars. These objects serve as cosmic beacons, their light enduring a multi-billion-year journey to reach us, though it dims at great distances. Until now, only a few galaxies have been detected at such vast distances, their presence revealed by the scant light preserved by space travel. But the fortuitous positioning of a star that amplifies its light has opened the door for us to see it. So, meet gravitational lensing, nature's own magnifying glass. This phenomenon occurs when the gravity of a massive object, such as a cluster of galaxies, distorts the space around it, bending the path of light from objects behind it, much like magnifying glass bends light to a focal point. Arundel's discovery is a textbook example of gravitational lensing in action. Located behind a cluster of galaxies known as WHL 0137-08, Arundel's light has been bent and amplified, allowing it to reach us across the vast expanse of the universe. Without this natural magnifying glass, the star's faint glow might have remained hidden and its mysteries unsolved. The importance of gravitational lensing goes far beyond Arundel's discovery. It's become an indispensable tool in the astronomer's kit, allowing us to study objects that would otherwise be inaccessible to our most powerful telescopes. With lensing, we can observe the detailed structure of distant galaxies, observe events such as supernovae in the early universe, and even search for dark matter by mapping the invisible mass responsible for the lensing effect. Gravitational lensing also allows us to test the limits of our understanding of physics. It provides a natural laboratory for studying the behavior of light and gravity, offering evidence to support the predictions of the general theory of relativity. The role of this phenomenon in the study of distant celestial objects is crucial. It not only magnifies the light, but also stretches the images across the beam of view, providing multiple angles of observation. This can reveal details about the structure and motion within these distant objects, offering a more complete picture of their nature. Thus, the cosmic quirk, predicted by Einstein's general theory of relativity, opened a window into the distant universe and was the key to the discovery of this star. Delving deeper into Arundel's personality, we uncover the story decoded by photons traveling through space. The Hubble data is the Rosetta Stone that turned these ancient signals into a story of the properties of stars and cosmic conditions. From the data collected by Hubble, scientists have concluded that Arundel is not only old, but extremely bright, far surpassing the brightness of our own sun. Its brightness suggests that it is a massive star that burns its nuclear fuel rapidly and lives a fast and furious life by cosmic standards. The Arundel light spectrum bears the fingerprints of the elements in the star's atmosphere. These spectral lines are a clue to its composition, showing that the star probably formed from the primordial material of the early universe, not enriched with the heavy elements that characterize younger stars, such as our Sun. The significance of the Arundel find cannot be overemphasized. As a star at the dawn of the universe, it provides a rare glimpse into the era known as the Cosmic Dawn, a time when the finest stars and galaxies formed, forever changing the dark, blank canvas of our early universe. During this formative period, the universe was a place of profound transformation. The first stars were the creators of the first heavy elements, the building blocks for everything from planets to life itself. The baton of cosmic discovery passed from the venerable Hubble to the James Webb Advanced Space Telescope, and that represents a huge step forward. It's given us a better look at Arundel, the most distant star ever observed, and thus opened a window into early space. Originally discovered by the Hubble Space Telescope, the true nature of Arundel remained an agonizing mystery. Was it a single star, a dense cluster, or something else entirely? JWST has now dispelled the ambiguity by confirming that Arundel is a single celestial body, possibly a star system with a main bright star at its center. Through spectral analysis, JWST has painted the star in its true colors. It is a B-type blue giant, a stellar giant with a temperature of 13,000 to 16,000 Kelvin and a luminosity nearly 1,000,000 times that of our Sun. This colossal star, similar to Regulus and Algulus of the Milky Way, is a testament to the grandeur of stellar evolution. JWST's revelations go beyond Arundel. It shed light on the galaxy in which the star is located, known as Doga Rising. This galaxy, named for its shape, is believed to be the most enlarged galaxy discovered during the dawn of the universe. Gravitational lensing, a phenomenon that turns massive galaxy clusters into cosmic magnifying glasses, amplified sunrise arc's light by 1,000 of times. This effect allowed JWST to observe not only Arundel, but also the surrounding bright star cradles, providing clues to the formation of early galactic structures. These observations have opened up a lively region of space with young star clusters less than 5 million years old, actively producing new stars. JWST's research on these clusters may one day solve the mystery of globular cluster formation, an enigma that has puzzled astronomers for decades. Arundel, a star of immense brightness and age, is not an isolated wonder but a key to the broader cosmic landscape of its time. Together with neighboring objects, it forms a puzzle that, put together, can reveal the conditions of the early universe, a time when the cosmos was a frontier of formation and transformation. The area around Arundel is a field rich in data. The light from these objects carries signatures of a young universe, encoded in wavelengths stretched by the expanding fabric of space. By analyzing this light, astronomers will be able to decipher the chemical composition of the early universe, understanding the prevalence of elements and the conditions that led to their formation. The vicinity of Arundel is particularly intriguing because it represents the region where the first galaxies formed. Stars in these galaxies are candidates for what astronomers call population 3 stars, hypothetical first-generation stars born from the primordial gas that filled the universe after the Big Bang. The search for population 3 stars is one of the holy grails of modern astronomy. These stars, formed from the pure hydrogen and helium of the early universe, were massive, hot, and short-lived. Their existence is key to understanding not only stellar evolution, but also the epoch of reionization when the opaque universe became transparent to light. The discovery of a population 3 star would be akin to the discovery of a living fossil, an object that, against all odds, provided direct evidence of the first chapter of stellar evolutionary history. Such a discovery would confirm theories about the early universe and provide unprecedented insight into the birth of the first complex atoms. Arundel, while not a population 3 star, is a beacon pointing us to this elusive population. Its existence in the galaxy since the origin of the universe suggests that we are looking in the right places, that remnants of these early stars may be hidden among the data that we're already collecting. In their quest to unlock the secrets of the early universe, Arundel and his contemporaries are more than just points of light. They are breadcrumbs leading us back in time to the very threshold of the cosmic dawn, where the first stars ignited the darkness and lit the universe with light.